here.
There. I was gonna say I'm not getting any. All right. So we're ready to go. Hi, my name is Eric Nielsen. I'm Senior Director of Social Media and Communities. We're at a VMware Code community event. We run community events all year long. It is our developer program, and we just do fun developer stuff, but some of it is a lot more serious. Some of it is fun. We run events. We live stream everything. So if you ever want to watch our sessions live, you can go to facebook.com/VMware Code, and there are all our live streams. So we're live streaming today. Hi guys, how's it going out there in the Ethernet land? We get usually 10 or 15,000 people watch every one of our live streams. So by us scanning you, we'll send you the schedule for the next year on when we're running kind of cool sessions and what the live streams are. So today we're going to talk a little bit about the makerspace and the sensors and what you need to know about sensors to kind of get started with Raspberry Pi. Before I do that, I'll just take a minute and talk, why is VMware here? Why do we care about the edge, right? Because really, our strategy is any app, anywhere. That is what it is. Any cloud, AWS, IBM, Azure, what are the other ones? Google. Oh yeah, Google, my favorite. So we do this. We have products that are on AWS. We have Wavefront, we have IoT, we have Cloud Health, manages AWS workloads. We have products that run on-prem, and we have products that run out on the edge. Like my favorite is Toyota and Honda are using VMware to manage cars. Starting in 2022, all the devices and all the sensors that are in cars are going to be managed through VMware software, right? So when you drive in the dealership, all the updates for these sensors and the drivers will come from VMware, right? So this is why we care. We care about the edge all the way up through your data center, all the way into the cloud, right? So that's just a little bit why we're here. Just to show commitment, we run a hypervisor called ESX. We care about ARM, we care about small processors. We've actually put ESX on Raspberry Pi. So back here I have a Raspberry Pi running showing ESX. So you can put VMs of Raspbian OS in VMs and manage them. It's really a management strategy out on the edge. I wouldn't say that Raspberry Pi is a good product to run your edge management apps, but we are working with other companies that are building edge type solid ARM devices to help manage your data coming in from sensors into your data center. With that, I'll get into what are we doing here with Raspberry Pi. I start with Raspberry Pi. It's a 3B Plus. The Plus is just, it has Wi-Fi on it. So you can get a cheaper version of the 3B. It works, just doesn't have Wi-Fi. You just have to use a hardline or use a Wi-Fi USB dongle. So you can get into this business for $35, right? Pretty easily. And then I'm going to talk about, how you get where we are on these lab tables. How we are and where we are on these lab tables is I installed Raspbian OS, which is the Raspberry Pi OS. It's a Linux-based OS. It has things, it's ARM compiled. You have to go download it, but when you get a Raspberry Pi, you have to get an SD card. That's your storage. So an SD card, we got a 16 gig, SD card from SanDisk for like $6. Then you just put it in and format it. There is a formatting application from .org, SD.org, that gives you the SDcard.org, that gives you a formatter that just formats your SD card. Once you format it, you go to Noobs, which is the Raspberry distribution. You get it, and you just basically unzip it and copy the files right on the chip, and you've got your OS installed. So there is no big thing. You just put it on the chip. Then you put the chip in the SD slot on the back of your Raspberry Pi, boot it. It'll take you through the install process. All the bits are on there, so it just basically asks you questions about your network and so forth, and you have a working Raspberry Pi. On the Raspberry Pi, then, you'll notice that you have all these pins. All these pins are what we call GPIO pins, general purpose I/O, which means you can do anything with these pins. They're programmable. Yes?
While you're installing the OS on it,
yeah.
there's no monitor attached at that time.
There's no what?
No monitor on it.
You know, it has HDMI, so you put HDMI with a monitor. It has USB for keyboard and mouse. So, you know, when installed, it gives you a full graphics. Raspberry is a full computer. We're running our coffee screens and our things on Raspberry, and right there, they're just on the ground, sitting there running. We're going to tape them on the pole. So they're full OS, full computer. So you install it, watch it install. It takes you through GUI. You can do that. You can install it through SSH in if you want, but I would just hook a HDMI monitor on it and go from there. Does that answer your question? Yeah, okay. All right, so now on the pins, GPIO is general purpose I/O. So what we're really going to do is we're going to use these pins to connect our sensors, right? And I'll get into what those pins are, but there's power, there's ground, and then there's I/O, right? Some of these sensors only just send 1 bit of data, right? So they're very easy to use. Other sensors have buses that you have to configure with addresses to work with these sensors. So I'll talk a little bit about GPIO Direct, which is very easy to do, and then I'll talk about I2C, which is a little more complicated. So I'll talk about each of these in these slide decks. A little bit about Raspberry Pi GPIO. They run on 5 volts or 3.5 volts, but all the sensors will auto convert down. They all run at 3.3, but if you hook 5 to them, they'll bring it down to 3.3. But always Google your sensor. There's tons of articles on every sensor, so you can just read somebody's article on the sensor to make sure that you're doing it right. We'll talk about the sensors we have here. They're standard female to female, so that way you have pins out on your Raspberry Pi, males, and you have pins on the sensors. Away you go. Some sensors you buy online, be careful, they don't have the pins soldered on. So you have just a basic flat board. So the barometric pressure 180 in this kit, you notice it just doesn't have them soldered on. So in order to use it, you have to put them in and solder them on. So watch when you're ordering your sensors. About half the sensors you order on Amazon, each one of these sensors, this sensor kit has 16 sensors, and it was 20 bucks. So a sensor costs about $1, right? Maybe $2 depending on how much you're buying it. Moving on. So drilling down on the Raspberry Pi, let's look at the sensors. It's good to look at the GPIO pins, kind of see what they do. So you notice on this we have pin 1 is a 3.3 volt positive power. So we have power because each one of these sensors will have to have a power and a ground, right? So let's see, my favorite is this guy. This is a proximity sensor. All it does is it has power, red. It has ground. I have a blue, sometimes black. And then I have yellow, which is data. Because this is GPIO, it's only going to send a positive 1.5 volts down the line when there's somebody in the room. That's all it does. It just sends a positive 1.5 down whenever the sensor goes off, which is infrared. So very easy. All you would do is connect it to a GPIO, set the I/O pin for read, and then you just go read it and see what it says. And if it says there's 1.5 volts on it, it means you've got somebody in the room because it's going off. If you put your hand on it, cover it, it goes off, it goes to 0 volts. So very easy, these pins. But now, as I said, that's a simple GPIO, basically connect and read the pin and read the voltage. But if you want, you can use I2C, which is a bus-oriented protocol, right? So it means that you can have multiple devices on that bus. We'll talk about how many devices you can have in a minute, but then I'm talking through a bus protocol to those devices. So some of the more complicated devices that have a command set, like the barometric pressure, it actually reads 2 different things, barometric pressure and temperature. And then it has a command set for when you talk to it serially through I2C, a bus protocol, you can send it commands like tell me the barometric pressure or tell me the temperature. So I2C bus protocols are usually because you have more complicated sensors, or you're going to have a lot of them because I can have up to 127 sensors wired in a bus configuration, and then I can address each of those sensors that way. So that's the difference between I2C, a bus sensor, versus a simple GPIO single line sensor. But the GPIOs are programmed, and on the Raspberry Pi you can see that some of these pins can be programmed. So pin 3 and 5 are actually an I2C bus. So those are the clock. For 5 is SCL, which is clock signal, and then the data signal. And that's the 2 lines for the bus, and then I have to have power and ground. So those pins on the Raspberry Pi are for I2C. But they're also general GPIO. So depending on what I want to use those pins, I can configure them for either just GPIO or I can configure them for the bus protocol, right? And we'll talk a little bit how to do that. We have UART, which is another type of bus, a protocol to talk. We have SPI. SPI is another bus protocol. It only allows you to have 2 devices on a Raspberry Pi because you have to have this 24 and 26 CE is the data connection per device. So the Raspberry Pi only has 2 data collection pins. If they had CE 0, 1, 2, 3, 4, 5, 6, you could have 6 on that, but you need that pin to make a SPI device work. I don't have any SPI devices in the sensors we're giving away. And then we have IDE PROM. That's memory. It's just reading memory. So if you want to read memory, you can connect a memory device to it and pull data from a memory device. So that gives you kind of the layout of the pins. So we've talked a little about GPIO. We use 2 protocols in these labs. One is GPIO and one is I2C. GPIO is a type of pin found on the integrated circuit, blah, blah, blah. I'm going fast because we only have half an hour to get through this. I want to get to the code. It runs at 3.3 volts and 5 volts. A lot of sensors have a regulator built in. We talked about that. GPIO requires software for specific sensors. So the data comes back on my favorite, which is the sensor. The data comes back as a voltage, and it's an analog voltage, right? So it can vary. So there are people that have written little Python sensor code objects that will allow you to interpret that data to mean something. On this guy, it's just 0 or 1, so it's an easy one. But other data sensors will give you data like this is a sound wave sensor. It is also GPIO, right? But it gives you an analog signal that's quite different, and you have to interpret that analog signal. So you generally, if you're going to write Python code, you want to go find the Python library, and everyone has written Python libraries for every single sensor that exists on the planet. So what you're going to do is you're going to go look for the Python code that's for the particular sensor that you want to get, and then just use the library that has that Python code in that, and that's how you generally will start writing Python code for the sensors themselves. So on this one, I just give the example of, look, on the infrared motion sensor, high on the pin means that it's sensed, low on the pin means it's not sensed. So you don't need much of a driver to handle that one. But on things like, this is a joystick XYZ, you just get data on position, right? So you don't really do much with it, and you have to figure out what to do with it. There's an analog to digital chip you can get with this that will turn it into digital data, but if you don't have that, it's just voltage signal depending on where you're moving the joystick. So, but again, there's good tutorials online for all these sensors, and so I'm just kind of covering some of what I know. The I2C sensors, a little more complicated because it's a bus protocol. Bus protocol has to have a timer. So one of the clocks is a clock signal, which times it. So if you look at pin number 5 here, I2C, that's the system clock. So that's clocking the bus, and then the data that's moving across is on pin 3. So for an I2C, all you need is pin 3, 5, and then a voltage and a positive voltage and a ground. So if I look at my Raspberry, and this is not the right one. That's not the right one. This one. I have 4 lines, right? This is the barometric pressure sensor. It's an I2C sensor. Has a command set. It has positive. It has power, and it has clock, which is green, and data I put on yellow. So I wired all my sensors when you get free ones. That's how I did it. Bright color is power, black color is ground, yellow is always data, and green is usually the control or something that you're doing. Another one that's interesting, well anyway, this is the sensor, this is the sound sensor. This one is not an I2C, it's a GPIO, but it has 4 pins because this one's not on all the time. It's not sending data. You put power and ground, and then you have a trigger. It says on here trigger. And what you do is you send a 1.5 volt down on that from a GPIO line, and that tells it to go take a snapshot. And so that's the trigger. It's like a shutterfly. You snap it, and that'll cause it to go get that, and then it has the data back, right? So the data back is, I think, labeled echo. I can't see it anymore. And that's the data back. So trigger, data back. It's not a serial bus, still not. Anyway, back to I2C sensor. The I2C sensors, you can have 128 addresses. It's a 7-bit address on those sensors, so you can have a large number of devices on a I2C bus. So if you have a robot or something that's going to have a lot of sensors on it, you can use the I2C pins on your Raspberry Pi to have multiple sensors, but you got to wire them in a bus, right? You got to loop them from sensor to sensor to sensor. So just know that. But they're good for command sensor because you're sending the data serial. It has a header, it has a packet, it has a data mode, it has a footer. So it's basically communicating on a protocol, which is the I2C protocol. Example of the address, it gives you an address which you can address for each sensor. You can only have 2 of any one sensor because these sensors are hard-coded in on an address. The sensor itself comes with an address, which is why if you get the libraries have the addresses already built into the library for the sensors, but you can add a sensor 1 and a sensor 2 on I2C. So the Y position of the 7-bit address is actually which sensor, and you can have a 2, 0 or a 1. So you can have a 0 sensor or 1 sensor. So in your bus, you can have 2 barometric pressure sensors, and you can have that address in there. You have to modify the library that you get to have the address for your 2 sensors, because generally the libraries think you're just going to hook 1 sensor up, and it's going to be the default address, which I think is 0. So it'll be the 0 address.
There's no software way to change the address.
No, you have to do it in the driver. Yeah, in the code.
It's really in the hardware. The address.
Yeah, the address is in the hardware. Yeah. Yep. So sensor highlights. So these are some of the sensors we're giving away that we have. That you'll get some sensor cards when I'm done here. You can pick up sensors. If you watch as many sessions as you want, you can come back. We're running them all week. We'll give them away till we're done. I got like 2,000 sensors, which is 40 chairs times every session that we're running. So I should have enough to give everybody a sensor every time they sit and watch a session. The BMP-180 is a barometric pressure sensor. It doesn't do, I think it's a single function, I forget. I'd have to read it. I think it only gives barometric pressure, it doesn't give temp. These bigger ones we have do both that. The interesting thing about this guy is it's not soldered. So we brought some of the BMP-280s, which are soldered, just for fun. Along with that, we have a temperature humidity sensor. We have a carbon monoxide sensor, a touch sensor, just fun. Now here we have what the communication protocol is, and kind of what the data range is that you get back from the driver, right? So you should be able to see that data and know that you're getting the right data when you're doing the lab. Again, these are GPIO, so it's pretty easy to get the data back from the sensor. And then what the pinout is on the sensor itself, so you know how to wire the sensor. So we have this deck out on the Maker Lab table, so if you get a sensor and you want to play with the sensor. I also have a blog that I'll publish this on. It's the code blog on VMware.com. So blogs.vmware.com/code will have this up on it later tonight. Photo light sensor, vibration sensor, gas sensor, motion sensor. I'll give you a minute. I'll stop talking for just a second. I can tell by Thursday I'm going to be hoarse.
How's the photo light sensor work? It detects level of light or just on off?
No, just motion. Oh, where's the light? Oh, light sensor? Where photo light sensor? Let's see. No, it gives you a value of how much lights it's receiving. So it'll give you an analog signal, which your driver will convert to a digital signal, a digital value. And I don't know what the scale is. I don't have the scale here, but you can Google the scale to see, or you can just look at your data. No, it's not on off. That one is an analog voltage level, increasing based on how much light there is that it's giving on the spins. So you basically read the analog line, which is just a voltage level, and then you interpret that voltage level to be how much light you're seeing. And the driver does that. If you get the Python driver, they have that built in. Some of these things have numbers that you can adjust. So if you know you're in a super bright environment, you can go in and you can edit that number so that it's evaluating it slightly differently. The makerspace tables behind us are Raspberry Pis. We have 15 Raspberry Pis with IP addresses set up with the pinouts there. We have 2 proctors that can help you get set up. If you want to get your things and mess around this week, we're here all week. You can play with them and learn, and there's nothing like doing it to see how it works to get that data back. I got 8 minutes, that's fine. So that's what we have. We have two different lab types. We have Leota, which is an open source implementation that has kind of a pluggable framework for Python code. So if you're not really wanting to write a bunch of code, you can go get the plug-in code, and it gives you an infrastructure that allows you to manage your devices. And they actually have written a GUI that helps you manage the devices so that you can drag and drop your device onto a frame. As long as you wire it right, you don't have to write any code. But if you're interested in code, I'm going to talk a little bit about the Python code that we have for both an I2C and an IOC device. So I'm going to skip that, but if you're interested in the open source Leota project that we support, as well as our products we have for small devices, you can talk to the proctors. They'll take you through some of that. Those things will automatically update that data onto AWS, and you can graph it in Wavefront, which is our graphing software that runs on AWS. So we have a product that we run there. You can do that if you want. So getting into the Python self-paced labs, I'll just show you some code. So I come back to my favorite little sensor here. You have to log into your Raspberry Pi. I mean, you don't have to, but you really need to. You can either edit it if you know VI, or you can edit it on your system and then SCP it over. And I give you the commands on how to SCP something over onto the platform. We don't have a visual editor on all these Raspberry Pis. We'd have to have too many monitors, and we didn't have that big a booth. So we just left them you SSH in or you SCP in from your computer. So here's the code. It's pretty easy. The Raspbian OS comes with an RPI GPIO library, which controls all the GPIO pins, right? So, and when I mean control, I mean set them up. Do you want them to be a SPI? Do you want them to be I2C? Do you want to use them as just general GPIO? Do you want to use them as, whatever. So you can turn those pins from GPIO to SPI, GPIO to I2C, and so we import that library that will then control our GPIO pins. That's on Raspberry Pi already. You don't have to do any install. I import the time library so that I can keep track of how often I'm doing things. No, that's nice to have. This is just standard Python stuff. But then notice I imported RPI GPIO as IO. That's a pointer to my object for the library I bought in. So then I'm just calling the methods for the IO library, the GPIO library. So first thing I do is I set the board. I say I want to be programming on pins on GPIO. So I want to make sure my board knows about GPIO. In fact, that's what I'm going to do here. So I just set the whole board to GPIO. And then I say, set up pin number 40 to be IO in. So a GPIO pin can be either input or output, right? You can read or write to it. You can't do both. You have to tell it. Now you can, in your program, set it one read and then set it another way write, but you actually have to tell the pin at the time you're going to use it what I'm going to do with that pin. That's important to know because otherwise things get a little wonky. Especially if you're using LEDs and odd other things, you have to keep track of your ons and offs, or ins and outs on the IO pins, right? So in this case, I'm setting it to IO in. That's all I have to do. Now I can just do a read, which is IO input 40, which is just says, go get me the input on pin 40. And that's it, that's my read. I put it in an if statement so that if it's 1, which is if IO input is true, that means there's a voltage on it, because in binary 1.5 volt is a 1, and so we get a true, which means it's going to print ICU, which because when this guy is got a voltage on it, it means somebody's in the room moving, and you'll just get a voltage on that, and that'll come back as a high, which is a 1, which means it'll print ICU. And then if you put your hand over and wait for a minute or so, run it again, or just put it in a loop, it'll go 0 because nothing is moving, because it's a infrared temperature sensor, so it gets used to your hand temperature and it just sits at 0. And so that's all the code I need. Then I say if it was 0, I just tell else print all quiet, no motion, right? So that's all I'm doing to use this controller on my Raspberry Pi. Pretty simple to do. Python has a GUI interface. It's pretty easy to use, so if you want to write a little GUI to do something with it, you can. Or you can proxy serve that data up from Wavefront, put it up on AWS and graph it in Wavefront if you want to. So this one is pretty simple to use because it's just reading the pin, looking at the voltage, and then doing something based on that voltage. So that's where I'm at with that one. And you notice I skipped over the Pinouts. Yeah, pretty easy. I think I talked about that. Okay. Now this one is the barometric pressure sensor. It does run on I2C, which is a protocol, and you have to do a little extra work here to make this work. A wire PIR 5 volts on pin 4, ground pin on 39. The system clock is STL trigger clock is on pin 5, and data echo is on pin 3. This is an interesting sensor. We have them all on the tables in that it will run both I2C and SPI. So that if you read the pinouts on the sensors, almost all the pins are always labeled. You just have to have young people eyes to be able to see it. Yeah, and it's up here, VCC, ground, SCK, and SDI. But notice it also has CS and SDO. That's because this will run SPI and it'll run I2C. So this is a dual protocol sensor. So we had to know that SDI actually goes to let's see, which one does it go to? It goes to 5, which is the data, right? Which SDI doesn't say data. Most I2C will say data on it. So, but because this is a dual protocol sensor, it doesn't say data, it says SDI, I think, right? Which is a SPI labeling, but they dual use the pinouts on this one. I think the BMP 180 does the same trick. So yeah, that's interesting to do. But anyway, that's how you wire it. You have to read that on the line that it's a dual sensor protocol, does SPI or does I2C. In fact, it says it. Oh, there you go. BMP, SPI, or I2C. So that wasn't hard to find. Now the code: import time, import board, import bus I/O, import Adafruit BMP. This is a library that somebody wrote to just control the BMP sensor. It's a full set library that you import and assign an object. Then you can use that library to reference the object and pull data from that object. So yeah, I'm not writing a lot of code to be able to do this. If you took a University of Wisconsin sensor class like my son did, who's a hardware engineer, he taught me a lot because he's like, yeah, we wrote our own drivers. Like that was part of the 4-month curriculum, is to actually write your own driver to pull the analog signal, interpret the signal, and so forth. But if you don't want to do a hardware engineering degree, just go get the library. So we input the Adafruit BMP 280 library, which is a Python library. Then all we're doing is create the object using the bus I2C port, bus IO, I2C board.scl, board SDA. You call the Adafruit library with passing in, am I missing something? I2C, which is your object, which is the board. So you create a board for I2C, then you just pass in that object to the BMP 280 library, and you're good to go. You now have an object that references the data, the command set, the addresses for the actual sensor itself. If you want to modify that, Python is just Python. Oh, I should say up at the top here, we actually had to go install that library, and I give you the command sudo pip3 install Adafruit circuit Python BMP 280. So a lot of these libraries are out on the net. You download them, you install them on your Raspbian. Now you have that library. You can use it to write your code, and that's all you do. The rest of this is the SPI code. If you wanted to use SPI instead of I2C. Then all I'm doing is setting a base level pressure by doing a BMP 280 C level pressure equals, and that's setting it in the library object itself, so it does a better job giving you the barometric pressure for your elevation. So they have that built into the library. Then all you need to do is run a loop that says print out the temperature and the pressure, and all you're using is the BMP 280 object, pass in that I want to get the pressure method, and it'll go get the sensor, pull the data, do the serial communication, send the address for the pressure versus send the address for the temperature, get those, load those in, and you're done, and that's how that works. So we're running out of time, so I'll just say this is where you can go. You can go join code.vmware.com. You can go look at a Wavefront blog on how to do sensor upload to Wavefront, which is on our code blog. You can go look for the blog on this session. I'll upload it later tonight. It'll be on blogs.vmware.com/code as well. It'll be one of the top ones. Nope, you have to, yeah. This was supposed to be a London Royal Society bench. Did you guys ever know of the London Royal Society talks? where William Faraday in the 1800s did talks, where Friday afternoon talks, and he showcased how magnetism worked. So the brick wall with the bench that looks like this, if you go Google it, that's what this looks like. He stood in front of everybody. They didn't have projectors at the time. And then he had his lab, and he did his lab, which is why I'm standing in front of the projector, because I'm old school and I believe in PowerPoint and video presentations. Sensor licks, if you're interested in this stuff, this Raspberry Pi Top 50 sensors is a great one. They have touch screens for like $20, so if you want to make a whole thing, you can make all kinds of stuff with that link. And then if you're interested in getting all of the sensors without sitting through a million presentations, this whole sensor kit is $20, so don't worry too much if you don't get the sensor you want. And that's all I got. So any questions? All right, well, great. I'll give out sensor cards and go to the front desk and pick up a sensor.